All right, let's get started. So, today and Thursday, we'll finish up lecture. Um, there is discussion this week on acid and base calculations. The yeah, um, next Tuesday, the 13th, is our final. So I have my office hours on Monday and Tuesday listed. There is homework because I don't want to I want you to focus on the test, but it may be useful. Homework is due after the test on Friday, 5/16. You should probably try it before. One of those is already open, the one on acids and bases. All homework, so all late homework, whatever, closes on 5/19. Okay, on 5/19 it closes, and grades will be posted by 5/22. I have already started grading the test number 3 that you had on Thursday. So hopefully you'll get that by Thursday or the weekend at the latest. The final, like I said, is the 13th. No notes allowed. I have on the right the equation list that you will be given. Okay. Actually, one of these you don't. Well, that's math. One's redundant. I also have posted a practice test, but just don't go off to the practice test. You should probably try out the blank tests from number 1 through 3, right? So I reposted those. Or 1 and 2. Number 3 will be posted soon once there are a few taking makeups right now. So once that's done, I'll post those. And then I'll office hours. All right, so this is everything that's on the test. Remember at the beginning, we started with thermochemistry and thermodynamics. That was test number 1, okay, in red. What's thermochemistry about? Heat, energy, right? So it's the energy associated with reactions. Then we went on to kinetics. That's chapter 12. What's kinetics about? Speed of reaction, the rate of reaction. Then we had for test number 3 that mechanisms, equilibrium, and acid bases. We're going to finish up chapter 14 now, and then we are going to move on to solubility. All right, so we're going to we finish acid base calculations. The last 4 things on there, we're basically just going to go at a high level and just talk about them. You will more than likely go into those more detail in some of your later time. And one thing that we will talk very, very briefly about, electrochemistry, we won't go into much. I'll just kind of give you an idea of it. But electrochemistry is really important. Why? What other word starts with ELECTR? Electrons, electricity, right? This is how we get electricity, right? So this is pretty important, but we'll talk about it. All right, questions on the final. All right, let's move on. So last Tuesday, we talked about acids and base calculation. So how to find pH of a acid or a base. And that really depends on when it's a strong acid or base or a weak acid or base. So if it's a strong acid or base, that means that whatever you're told let's start with the acid. If you're told that it's 2 mole or 0.2 molar acid, that means it's 0.2 molar H plus. And so you can just plug that in to find the pH. If it's a strong base, let's say you're told that it's 0.2 molar NaOH, well, that means it's 0.2 molar OH minus, which then you can find H plus using this equation right here, and then plug that in to get the pH. Weak acids and weak bases are different. Why? What's the difference between weak and strong? Strong, fully ionized, whereas weak, partially ionized. So we can't do that. 0.2 molar of a weak acid will not get you 0.2 molar H plus, right? 0.2 molar, let's say HF, which is a weak acid. This will not get you 0.2 molar H plus, right? You're not going to get that. Instead, you need to use an ice table to calculate H plus. Then you plug that in to get pH. For a weak base, let's say we have 0.2 molar NH3, which is ammonia, which is a weak base. You use an ice chart to calculate the OH minus. Then you calculate H plus from that. And then you calculate pH from that. We did examples on those last time. You're going to do examples of them in discussion this week, or you already have. And that's your homework. Homework number, I forget what it was, 10, which is due after the test, but you can already do it now. Okay. All right. Questions? All right, so we're going to move on to what are called polyprotic acids. Okay. All right, so polyprotic acids are important because an example of a polyprotic acid is amino acids, which are the building blocks of protein, right? All right, so let's talk about what an acid is. An acid is a compound that donates an H plus to another compound. Okay. Let's say I have HCl. HCl is acidic, is an acid. And so we can call that H plus an acidic hydrogen. An acidic hydrogen is one that dissociates. Okay. But not all hydrogens are acidic. For instance, if I have CH4, which is methane, which if you turn on your gas grill at home, methane will come out. It's also known as natural gas. Methane is this compound right here. It doesn't have any acidic hydrogens. So none of these hydrogens are going to come off, right? The Ka for that reaction up there is 1 times 10 to the negative 56. Okay? We were talking about weak acids of being like 10 to the negative 10. This is 10 to the minus 56. This does not happen, right? You don't lose one of these H's. Now, the reason for this, you'll talk more about when you go on to OChem, if you go on OChem, and most of you will, right? It has to do with what the hydrogen is bound to, right? In this case, the hydrogen is bound to the carbon only. Whereas in this case, the hydrogen is bound to a chlorine. And chlorine, if you remember correctly, right? Chlorine is a term we used in Gen Chem 1, electronegative. That means chlorine really wants electrons. So if chlorine really wants electrons, it's going to steal an electron away from it, and the H plus is just going to leave, right? But you'll learn more about that in a lot of detail in OChem. All right. So we can have what we call monoprotic acids. Monoprotic acids have one acidic hydrogen. This can either be because they only have one hydrogen, like HCl, right? HCl can't lose 2 hydrogens because it only has one. Okay? Or If it's something like this is ethanol, CH3CO2H. No, sorry, this isn't. This is not this is acetic acid. If I have CH3CO2H, this only has one acidic hydrogen. So it only loses one of it. This is due to its structure. Again, you don't need to know why, right? You'll learn about later. These hydrogens here are not acidic. All right, so monoprotic, one proton, so it produces one H plus. We can have polyprotic acid. Polyprotic, poly meaning many, protic meaning proton, so it produces many H pluses or more than one H plus. So we can call it diprotic or triprotic or tetraprotic or pentaprotic. If you remember your prefixes, diprotic means it has two H pluses, and triprotic means it produces three H pluses. Those are the only, we're not going to deal with tetra and penta here. Sometime. All right, so an example of this is H2SO4. H2SO4 is sulfuric acid. H2SO4 is diprotic. It produces two H pluses. How does it do this? Well, it does this in stepwise ionization. That means it doesn't do it all at once. So first, H2SO4 will lose one H plus. It'll be left with HSO4 minus. Okay. It lost an H plus, so that means it had H2, now it's H, and then it went from a neutral to being negative. And then that second one can lose another H plus, and it become SO4 2 minus. All right, these are both reversible reactions. So what does that mean they both have? They have K values, right? So this can be a K, and this also is K. We call them KAs because they're acids. And we call the first one KA1 and the second one KA2. The first ionization, right? So we call this the first ionization because it's losing its first H plus. It has a Ka1 of greater than 2. So we would call this a strong acid. The second ionization is now 1.2 times 10 to the negative 2. That is much weaker. Right. This kind of makes sense, right? Let's say, you know, I have my wallet, I go to the subway or something or wherever I'm walking out to, and I lose my wallet. Okay, someone pickpockets it. Okay. Well, do you think in the future it's going to be easy to pickpocket from me? No, I'm going to be like, oh, okay, I'm not going to wear it in like an outer coat. I'm going to put it in my my pants or something, so that way people can't steal. Right. Well, losing that first H plus is easier than losing the second H plus. Why? Because now I'm trying to take something that's positive away from something that's negative, right? And remember, negative and positive, those are attracted. So try taking something away from this is much harder. And that's why the Ka2 is much smaller than the Ka1, right? Here, you're taking away an H plus from a neutral compound. Here, you're taking it away from a negative compound, right? So it gets a lot harder. All right, so let's say we have this H2CO3, that's carbonic acid, okay? I want you both, or you to write down the first and second ionization reactions for it, and then what are the Ka expressions for those? And ionization, what does it mean to ionize? It means to become an ion, right? So notice in this case, we're starting off with a neutral compound, and it's an acid, so it loses an H plus, and that leaves behind an ion. And so Ka1 is equal to the H plus times the HCO3 minus over H2CO. That's the first ionization. And remember what we said, it's stepwise. That means the second ionization will start from what we had at the end of the first ionization. So we start with the HCO3 minus and we go from there. All right, so what's left behind when HCO3 minus loses an H plus? CO3 2 minus, right? Losing something that's positive makes you more negative. All right. Could there be, I told you that this was diprotic, but could this compound, H2CO3, be triprotic? No, why not? you can't sue me and take away 2 cars because I only own 1 car, right? So if you're a acid and only have 2 hydrogens, you could only be diprotic. You can't be triprotic. Now, in some cases, H2CO3, just because you have 2 hydrogens doesn't mean you're diprotic. You may only lose 1, but the maximum you could be is diprotic. All right. It always is the case that the first ionization, Ka, is greater than the second ionization. So Ka1 will be greater than Ka2. It will be greater than Ka3, which we'll talk about in a second. And so at equilibrium, what happens is all of those reactions, reversible reactions occur. So you'll start off with H2CO3, and that's going to form HCO3 minus and CO3 2 minus, and then it'll be H plus and OH minus. And notice how you have multiple producers of H plus, right? But so that means both those reactions could determine the pH. But in most cases, Ka1 is so much greater than Ka2 that you can assume that all of the H plus comes from that first ionization, right? And that determines the pH. All right, now in some semesters, we actually go through the calculations to determine the pH and determine the equilibrium concentration. We're not going to do that here, right? But you should know that your first ionization, that's the one that determines the pH. All right, we can also have triprotic acids, right? An example of a triprotic acid is H3PO4 or phosphoric acid. It produces 3 H pluses. And in the same way that we said for diprotic, it's stepwise, the same thing occurs here. So first the H3PO4 loses 1 H plus to become H2PO4 minus. Then that H2PO4 minus loses another H plus to become HPO4 2 minus. And then that HPO4 2 minus loses another H plus to become PO4 3 minus, right? And so it's left with a phosphate ion. And as you can see, the Kas are listed on the right there. Ka1 is always greater than Ka2, and it's always greater than Ka3. And usually, Ka1 is much, much, much greater than Ka2, right? Notice that's 10 to the minus 3 and 10 to the minus 8, right? So is there a 5 order of magnitude difference between the two, right? So this is much stronger than the other two. Second, let me just. All right, questions. All right, now we've talked about polyprotic acids. So we talked about monoprotic acids. Monoprotic acids produce 1 H plus. We talked about polyprotic acid, which produce more than one. Okay. We can in the same way have monoprotic bases and polyprotic bases. And so if a monoprotic base or if a monoprotic acid produces 1H plus, a monoprotic base will gain 1H plus. And a polyprotic base will gain more than 1H plus. All right, so polyprotic bases accept more than 1H plus. And they're basically just the conjugate bases of your polyprotic acids, right? So if H3PO4 donates 3H plus, that means PO4 3 minus, which is what we ended with, can accept 3H pluses. All right, so phosphate, PO4 3 minus, is triprotic. Okay. We want to figure out the equations for the first, the second, and the third accepting of the H plus. Okay. So I want you guys to do this because it'll either be for polyprotic acids, bases, or something else. I want y'all. I say PO4 3 minus is a base. Okay. Write out the equation for PO4 3 minus gaining 1H plus. Okay. Where does it get that? And what is that equation? Okay. So PO4 3 minus is a base. Write out the equation for it. The first ionization reaction. The first accepting of H plus. I don't remember off the top of my head, but I'm pretty sure if you look at the practice notes, there's one that asks this exact question or something very similar to it. Where does that PO4 3 minus? It gains an H plus. Where does it gain an H plus from? Just an H plus floating around? No, this is. So let's think back. What state are acids and bases in? Not liquid, aqueous. They're aqueous. And everyone, maybe it's been a while since that. What does aqueous mean? It has water, right? So the PO4 3 minus is gonna get that H plus from water. Okay. And why not from just, hey, a random H plus? Well, that's because in this water here, there is some H plus, but there's a lot more H2O. So it's more likely for the phosphate to run into H2O than it is to run into H plus. Okay? So that doesn't happen, right? This does. And so this gains an H plus. And so if I gain something that's positive, I become less negative. So it goes from 3 minus to 2 minus. And what's left behind? Well, if this loses an H plus, I'm left with OH minus. And so then, therefore, we call this KB1 because it's the first addition of an H plus. This is going to be equal to HPO4 2 minus times OH minus over PO4 3 minus. And why isn't the H2O in there? Because it's a liquid, right? Remember, we never include liquids or solids in our K values or K equations. All right, so this is our first ionization. Our second would start off where we ended with HP4O2 minus. It's going to gain another H plus from water. And so that's going to become H2PO4 minus. This will be KB2. And then this can gain one more electron, or sorry, one more proton to become H3PO4, the phosphoric acid. And this would be KB3. All right, here they are again, right? So KB1, KB2, KB3. All right, now, let's go back and let's look here. HPO4 2 minus and H2PO4 minus, okay? In these equations, they're acting as bases, okay? Let's go back a few slides. Here, I have H2PO4 2 minus and HPO4 2 minus, and they're acting as acids. Okay, so there are some compounds that can react, that can be either bases or acids. Okay, we call these amphiprotic. An amphiprotic compound is a compound that can either be an acid or a base. Think of amphibians, right? I have a minor in biology, so I know a little bit. I remember amphibians, they could be on water or on land. So amphi meaning both or something like that, right? So amphi meaning it can be both gaining or losing protons. Okay. So those are examples. Another example is water, right? Remember, water, it can be both an acid producing H plus, or it can, in that case, it loses, or it can produce OH minus and be a base. Right? Some things are amphiprotic. HCl, it's the classic acid. It is never going to gain an H plus, right? This never happens, right? So HCl is not amphiprotic. All right, so I had one more problem, but you can do this on your own. So, if I say it's diprotic, you can write out KB1 and KB2, and KB1 will always be greater than KB2. Okay? All right, so that is it for polyprotic acid. Now, in the chapter, and some semesters, we actually go through the calculations, but we're not going to do that this semester. Okay. But I guarantee a problem like this, right, where I'm asking, hey, what is the equation or what's the reaction? That's going to be something that likely will be on the test. All right, questions on polyprotic acids or bases? All right. Now, we're going to today, and then we'll continue on to next time. We're going to talk about neutralization. Okay, so it's chapter 14.6 and 14.7. All right, so we've talked about acids, we've talked about bases. What happens when I take an acid and a base and I put them together? Okay, so if I have HCl, an acid, and NaOH, a base, the H plus and the OH minus are going to come together to form H2O, and I'm going to be left with NaCl. So neutralization is when an acid and a base react to produce water and a salt. Where a salt is an ionic compound that's formed from an acid and base. Okay. This is one of those annoying things where in everyday life, when we say salt or table salt, we're talking about NaCl. Here, a salt can be anything. So if instead of HCl, let's say this was HBr, well, then the salt that would form wouldn't be sodium chloride, it'd be sodium bromide. Okay. Both of those we would call a salt. But in everyday life, when we talk about table salt, we talk about NaCl. All right, so we're going to talk, this chapter 14.6, about a specific type of neutralization, okay? And these are what are called buffers, okay? So a buffer is a solution containing a weak acid and its conjugate base, or a weak base and its conjugate acid, however you want to think of it. So for instance, it could be HF, which is a weak acid, and F minus. Or it could be NH3, which is a weak base, and NH4 plus, which is its conjugate acid. Now, one thing is, I could go, well, I couldn't get that. HF, I can't go to that. If you've ever seen Breaking Bad, HF is the acid they use to decompose bodies, right? I always think in the pilot episode of Breaking Bad, the guy goes into his high school stockroom, and they just have cartons of HF, right? If I wanted to use HF, I'd have to go to the president of the university to get permission to have that, basically, right? It's so toxic. But let's say not HF, but let's say another weak acid. Let's say NH3, right? NH3 is a weak base. I could find solid NH3, okay? It's impossible to get solid NH4 plus, right? If it's an ion, it can't be a solid, right? If you have NH4 plus, you would have to have it in conjunction with a salt, or with in this case, an anion. So I wouldn't have NH4 plus, I would add NH4Cl, which would break apart to give me my NH4 plus. All right. So a buffer is a weak acid in its conjugate base or a weak base in its conjugate acid. Okay. What does buffer mean in everyday life? What? Something going between something, right? So let's say there are zombies outside, right? And we want to get them out of the room. We take all the desks and we put them up against the door, right? Because that would be a buffer, right? Or, hey, a friend asked me to dinner. I don't really like that person. I may bring along someone to be a buffer to kind of like, hey, you know what? If it gets in a weird situation, you stop, right? Stop it. Buffers are solutions that resist a change in pH when you add an acid or a base. So they resist changes in pH. Okay, so those are the two things you should know about buffers, like ingrained in your head. Weak acid, weak base, and they resist changes in pH. Okay, weak acid, weak base, and they resist changes in pH. Let's look at something that is not a buffer. Okay, pure water, which is a pH 7. Okay, if I have 1 liter of water, and all of a sudden I add in 0.01 mole of HCl. That HCl is going to produce H plus, right? And O and Cl minus. And the pH, I could do the math, would end up being pH of 2. Okay? That is not a buffer. I added in some acid and it changes dramatically from pH 7 to pH 2. But my blood is a buffer. My blood has a pH of about 7.4. If we took some blood and we added in some HCl, it might change to 7.3. Or if I added in some NaOH, a base, it may change to 7.5. Our blood is designed, or it has, or it is naturally a buffer. That is ridiculously important because if the pH in my blood changes by more than 0.4, my cells will die. Let's look at this a little bit. In your blood, you have H2CO3 and you have HCO3 minus. The H2CO3 comes from the fact that I breathe in CO2 or that I produce CO2. So I have H2CO3 and HCO3 minus. So I have a weak acid and its conjugate base. These act as a buffer in my blood. By the way, this is why if you ever heard, oh, you should drink alkaline water because it makes your body more basic, which means, or alkaline, right? Which means cancer can't grow. That's DS because you can't really change the pH of your blood. And if you do, that's a bad thing. Okay. And by the way, when they talk about that research, they say there's a forgotten German scientist that proved this in the 1940s. That was a Nazi, okay? And I've always learned if it started with Nazi scientists, I don't really believe it. Okay. All right. So let's talk about how this works. Okay. All right. So we have CH3CO2H. Oh, we're going to start with a different buffer, right? So let's say we have 0.1 molar acetic acid, that's CH3CO2H, and 0.1 molar of sodium acetate. Okay, that sodium acetate is going to produce 0.1 molar of my acetate. Right, so I have acetic acid and I have acetate. Both are present. And I know that the Ka is 1.8 times 10 to the negative fifth, or I'm told that. Well, let's see what happens when I add in an acid or I add in a base. So if I add an acid, H+, that's going to react with either the acetate or the acetic acid. Any ideas which? So H+ is either going to react with the acetic acid or with the acetate. Okay. All right. Well, here's the deal, right? H+, that's an acid, right? What do acids react with? Do acids react with other acids or do they react with bases? They react with bases. So if I add H+, it's going to react with my base, my acetate. And, well, if I have H+ and I add it to that, that's going to form my CO3CO2H, right? So I add acid and it converts some of my base, my weak base, into a weak acid. Well, what about if I add my OH minus? If I have OH minus and it reacts all right, let's say I have my OH minus, and that OH minus can either react with the acid or the base. Which one is it going to react? The base will react with the acid. And so what happens is, well, the acid loses that H+, that goes to the OH minus, and I'm left with CH3CO2 minus. I'm just going to put a green square around this. Let's square around this. So if I have an acid, my base gets converted into acid. If I add in base, my weak acid goes on to produce my weak base. Okay, this is an arrow, sorry. Or it's supposed to be an arrow. All right, so that's how buffers work, right? They basically are a weak acid and base that are in combination, and they convert between each other based on whether you add acid or base, right? And that works to keep your pH constant, okay? And the key thing is that if you add the acid, all of that H+ will go away. If you add in base or OH minus, all of that base will go away. Let's look at this another way. Okay. So let's say at the beginning, I have equal concentrations of the acid and the base. Okay. They're equal concentrations. So that's why the bars are the same. If I add in some H plus, the CO3 CO2 minus gets converted into CH3 CO2H. So that increases, this decreases. But the key thing is all the H plus gets removed. Okay. If instead I add in H plus OH minus, that OH minus converts some of the acid into base. Okay. But the key thing is that my OH minus goes away. This seesaw, that is how they keep the pH from changing a lot. All right. Let's look at these. And I want you guys to figure out which of these four solutions, and there could be more than one, which ones of these are a buffer solution. Oops, sorry. I didn't mean to do that. Which one are we on? We're on this one. All right. A. Is a buffer solution? I hear no. Why? And it is an acid. HCl is an acid, and Cl minus is its conjugate base, right? But what do we know about HCl? It's a strong acid. So that's not going to be a buffer, right? And it's not going to be a buffer because remember, the whole thing with buffers is that the weak acid gets converted to weak base, or the weak base gets converted back to weak acid. The Cl minus is never going to be converted back to HCl. That doesn't happen. And so that's why that can't be a buffer. How about B? No. B is not, even though H2S is a weak acid and F minus is a weak base, but they have to be a conjugate. Okay? All right. C. ClO minus is a weak base, and therefore HClO is its conjugate acid. So this one is a buffer. And then finally, the last one. Okay? H2S is a weak acid. What is the conjugate base of H2S? So I take away an H, and it goes from H2S to HS minus. Well, this is NaH, NaHS. This in water is going to produce that HS minus. Okay, so that, oops, the wrong way. That is also a buffer. All right, we are pretty much one. Oh, I'm just gonna in this slide, I just make it a little more generic. So if I have my acid HA and my base being A minus, right? I have this interconnection between the A minus and the HA, right? A minus, if you add a acid, produces HA. HA, if you add an OH minus, gets converted to A. All right, so let's go ahead and let's do an equation or do a problem. Okay. We're not going to do the whole problem because again, I cut a little bit. But let's say we have a buffer with 0.1 molar acetic acid and 0.1 molar sodium acetate. Okay. We want to know what its pH is. We want to know what happens when we add in acid, and then what happens when we add in base. All right, so we have acetic acid. That's CH3, CO2H. We have acetate, CH3, CO2 minus. And we have H plus. Okay. Generally, if I had 0.1 molar and 0.1 molar of this, to figure out the pH, we would have to use an ice table, right? We've done this before. You calculate the Q, you figure out the shift, then you figure out whether these are minus X or plus X, you solve for K, and then you solve for X. Okay? But there's actually an easier way. And this is only for buffers, okay? So we're gonna learn this equation. I don't know if I give it to you. Let's see if I give it to you on the test. Oh, here it is right here. All right, so I give it to you, but you need to know how to use it. It only works for buffers, okay? It's called the Henderson-Hasselbalch equation. And what it says is that if you have, well, this is just rearranging it, we won't. The pH of a buffer is equal to pKa plus the log of A minus over HA. Okay, so pH equals pKa plus log of the concentration of A minus over the concentration of HA. This only works if X is small, so if the concentrations are much bigger than the Ka. And remember that pKa is equal to negative log of Ka, right? Because we said pH equals negative log of H plus, right? Well, if I have pKa, it's negative log of Ka. Right. This is the Henderson-Hasselbalch equation. It's very useful when you are dealing with buffers. Okay. I now notice that their molarity of A minus over molarity of HA. Can anyone tell me what molarity? What are the units of molarity? Moles per liter. Okay. Well, if the A minus is in moles per liter, and the HA is in moles per liter, and they're the same solution. They're the same solution, so their total volume is the same. So I can just get rid of the liters. And so that means I can also write this as pH equals pKa plus log of the moles of A minus over the moles of HA. Which one do you use? Depends on the problem. Sometimes you're given moles, you use the second one. Sometimes you're given molarity, you use the first one. Okay. But they're the exact same except the units are different. All right, so in this case, I can figure it out as the pH equals pKa. I'm given molarities, so I'm going to use molarities, plus log of the acetate over the acetic acid. Okay. So that's going to be negative log of 1.8 times 10 to the negative 5 plus log of 0.1 over 0.1. All right, so why don't you all figure out what this is, and then we'll review it. So negative log of 1.8 times 10 to the negative 5 is 4.74. This is 0.1 over 0.1 or 1. Log of 1 is 0. So it's just 4.74. Okay. So I can find the pH if I know the Ka and the concentrations of both the weak acid and the weak base. Questions? This is much easier than doing an entire ice chart, right? All right, let me just go back 1 second, all the way back to, I think it was slide 3 or 4, 2. Okay. All right. One of the hard things on a test, especially cumulative tests, will be that there'll be a lot of different ways to calculate pH, or in this case, a lot of different capital Ks, right? Always remember, especially in this case where you're given all these equations, go through and say, hey, when do I use this equation? When don't I use this equation, right? Because this equation that we just learned, the Henderson-Hasselbalch equation, will not work if it's not a buffer, right? So, and in fact, the first thing I do when I grade is, if I see something and it's not a buffer, if it's not a buffer problem, but I see Henderson-Hasselbalch, you pretty much get a 0. I say, okay, you don't know how to do it. So always go through it and make sure you understand when to use different things. All right, questions. All right, so let's see what happens if you were to add in some HCl, right? So let's say I added in 0.1 molar HCl to this buffer. Well, I'm adding H plus. So what does the H plus react with? The acid or the base? H plus is an acid, so it's going to react with the base. Okay. All right. So the CH3CO2 minus plus H plus is going to form the acid, right? And so in order to figure out the pH, you need to use an ice charge, and then use the Henderson-Hasselbalch equation again. We're not going to do that, okay? But I can tell you, if you were to do the problem, the pH would end up being 4.73. Okay? So notice what happened. You added in H. You added in H plus. You added in an acid, and the pH barely changed. That's what buffers do. Instead, if you added in the base, OH minus, it reacts with your acetic acid to form the base. Okay? And because you're adding in a base, the pH is going to increase to 4.75, but it doesn't increase a lot. That's what buffers do. We'll talk about, or I have this on a later slide, but now there is what is called buffer capacity. Buffer capacity is how much acid or how much base you could add before the pH starts changing a lot. Okay? So even though my blood is a buffer, if all of a sudden I inject in a whole bunch of acid, eventually the buffer loses its ability to stop the pH. Okay? And that's actually one of the things that they worry about in your blood, right? They look at your pH in your blood because that can show you either have too much CO2 or not enough. Okay. All right. Okay, so why are buffers important? We already talked about blood. Our oceans are also a buffer. Our oceans, we have CO2 in the atmosphere that forms the H2CO3, and we have rocks and soil that produce CO3 2 minus. And so the ocean is a buffer with a fairly similar reaction as we have in our blood. Okay. Now, what's happening though, unfortunately, and this is a good thing, right? Why? Well, I just said my blood, I don't like to have pH change a lot. Well, if you're a fish and you're swimming around, if pH were to go up and down, that would be bad, right? They can't. So the fact that it's a buffer is a good thing. Well, unfortunately, we're shifting this buffer slightly by the fact that we're putting more CO2 in the air. That goes in the water. So we have what's called ocean acidification, right? That hurts coral reefs, that hurts fish, fisheries, etc. Okay. And then finally, why is it important? Well, in lab, you use buffers, and also in a lot of things you buy, right? You may have on shampoo ads, they say it's pH balanced, right? Well, it's pH balanced to be at a pH that is good for our hair, right? Shampoos usually are at pH 5.5. And if I look at, this is just a random bottle, I see sodium citrate and citric acid. This is its acid, and this is the conjugate base, right? So inside there is a buffer to keep it at a pH that works best for our hair and doesn't damage it. Okay. All right. So that is it for buffers. Okay. You're not going to have to do calculations for what happens if you add or lose, but I guarantee there will be at least one Henderson-Hasselbalch equation. Okay. All right. Next time, we're going to continue on and we're going to talk about titration and we'll wrap things up. Okay. Any questions? All right. If you didn't sign the sheet, sign it there. Otherwise, I'll see you on Thursday.